Good morning, dear students. In this presentation, we look at the basic concepts like lexical conventions, data types, etc. And we will end with a small program, how it is run and how will be the output. So you can follow the reference Verilog HDL, a guide to digital design and synthesis by Samir Palnikar for more details. So first of all, the lexical conventions. Since you have already studied C, the representations here are somewhat similar to C, only slight modifications are there. This is a case sensitive tool, and you have some tokens like white space, comments, etc. are there. I will look at only the essential aspects associated with this. You can specify a blank space by a \b, and similarly tab and new line you can represent it with a \t and \n respectively. So when you start writing the program, the usage of these aspects will be more clear. The operators, there are three types of operators. One is unary operator, binary operator and ternary operators. So that means in unary operator you have only one operator. In the second case you have two arguments, and in the third case you have three arguments during the operation. Number specifications. So you are trying to represent a circuit diagram. So the representation or the behavior of the circuits need different type of representation. So they will be represented with sized numbers, that is the size of the number will be specified in the representation, unsized, unknown and negative numbers. So these are the features required for an HDL. See in more detail. So what are marked in red color, it shows that the syntax of sized numbers. Initially it gives the size, then apostrophe followed with the base, which number system it is, and the number as it is. So this is how it represents. And if you look at the example here, the first example 4'b and 1111, that means 4 is the size of the digits and b is the base. Here b represents binary, h represents hexadecimal, o represents octal, d represents decimal, followed with the number. Here 111 is the number in binary format. Similarly, a hexadecimal and decimal numbers are given. In unsized numbers at the right side you can see the initial size is not there, the respective part is available there. Here first example 23232 is there, that by default that number will be decimal. For other numbers you have to show the base of the number. So here the size of the number is not shown here. Please remember these numbers are sometimes represents the number of inputs and maybe some voltages, something of that sort. So in order to faithfully represent the behavior of a circuit diagram, these type of numbers are required. Another type is X or Z values. X is an unknown value and Z in lower case normally represent a high impedance condition. So you will study this high impedance condition along with your circuits that performs digital task. and you can represent negative numbers by putting an additional sign at the initial position or at the beginning of the number. And underscore is used normally to represent the data more legibly. Then another convention is strings. Here if you want to say display some text, in that case that text can be represented as a string. So here in the example, in double quotes, you can see a hello world. That is an example of a string. Similarly, you have identifiers. You will use a dollar sign before the identifiers. And there are escaped identifiers. If you use backslash and whatever things in between a backslash and space, even though they are identifiers, their meaning may not be taken. Sometimes it is used for naming the modules. And data types. There are different data types starting from nets, vectors, etc. are supported by the Verilog tool. Here we'll start with the value set strings. So here, to describe a circuit, sometimes the strength of the circuit or maybe some current carrying, you know, to represent whether the current will flow from module 1 to 2 or from 2 to 1, some conventions has to be followed. In that direction, this value level and value strength are being used. Here more details are given for the value set. The value levels can be either 0, 1, X or Z. 0 is logic 0, 1 is logic 1, and X is unknown, and Z is high impedance or floating condition. So in order, these are the characteristic of a digital circuit. So in order to represent this characteristic, these value levels are used. Even with those levels, there will be a strength level also to be used to for representation. They are like supply, strong, pull, large. These are some strength levels are used to represent the value set or value level. That to at different aspects. Another data type is called net. Normally when you write program, these keywords may be widely used in our initial programs. Here a representation of AND gate is shown. It has got its input B, C and the output A. So when you start with writing a program, you have to define the input and output. Here you can see in red color wire A that represent the output. It says that line, that connection is conductor is considered as is represented as wire A. And usually along in the examples or in the program, along with this you may use either it is input or output. And wire B and C, these are another category of wires, that is B and C are the inputs and A is output. And sometimes the value of the wire also can be specified. Logic level will be specified with say 0 value. Here 1 apostrophe B 0, that indicates one binary bit, that is and the value having 0. And registers, similar to the wire, you have register. The difference between wire and register is a variable with wire will not have any memory, but a register, a variable with register will have a memory. It is able to hold a particular value in the register. Here the example shows reg reset. That is, reset is the operator or maybe the name of your input or output, and reg is the type of that particular data, and the rest of the programs as it is part of usual HDL program. Now vectors. So here in this context, the input to any digital circuits may be of 1 bit, or sometimes it has multiple bits, or usually we represent or maybe called as bus, data bus, address bus, and so on. In that context, if you want to represent a multiple lines on a single input, you will be using the term called vector. Even though it may be a wire type, but it will be a vector by representing with that 7:0. That is, you have 7 lines, or it starts from 7 to 0. A bus is having 8 lines, so it is represented from 0 to 7 or 7 to 0. That is how it is been represented. And another type is integer. You have a provision to represent any value with a signed integer. So here it is a keyword to provide, maybe used in behavioral programming. Similar to integer, you have a keyword real is available, that is used to represent some values to variables. Time is another keyword, where whenever you want to track the timing, the time is a keyword directly used, and so that the timing of the simulator can be transferred to this variable. Similar to vectors, you have provision. Similar to C programming, also you have provision to represent variable with arrays. The syntax shows your data type, variable name, and start index and end index. Similarly, the memory, since it is a digital circuit, you will have to design or consider memory. You will have to represent memory. So in that case, you have a keyword called memory available. So it will be an array of registers. Similar to C, parameters are used. That is similar to constant. In C, we have parameters. That is, parameter with its name and value can be shown. Here the example shows parameter port ID equal to 5. So the value can be directly assigned to that port ID. And next is strings. We have already seen, if you want to represent some values or some text in the simulation, or to describe something, you need a provision for a string. So the string is represented like this. In double quotes, the string will be represented. And system task. Here 4 system tasks are shown here. One is display, monitor, stop, and finish. Because using this system task, you will be able to display the value of variables or wire registers at a particular instant, and monitor will give this value whenever there is some change happens to those variables. Stop will stop the simulation, but finish will terminate the simulation. Stop with some interactive mode. So whenever you use a system task, the dollar sign has to be used initially. For example, if you want to say dollar display hello world, hello Verilog world. So if you use this display, the value will be displayed in the console when you simulate the program. Same way, if you want to display some particular value of a variable, then say as example shows display dollar time, the output shows the content of the variable time or the time instance of simulation at the output, that is 230 here. Same way, you can stop or finish the program at different time instances. Another aspect is monitor. Dollar monitor will provide, if you give it at the beginning, say you can see a sentence written there, dollar monitor in brackets, the parameters name and other details. It will keep on outputting the values as and when we give the input, or maybe clock, something similar. So whenever there is a change happens to the input, the this monitor will output the data to the console. So the simulator will give the output. So when you do with hands-on with these programs, things will be more clear. Same way, other things are compiler directives. Define and include are compiler directives used similar to C. In C also they use for specific purpose. Similar thing is done here also. Okay, now I will show a simple program and its test bench and how the result we obtain. So now we can see in shaded area a module or2 data flow as a heading it is written. So here whatever there in that colored area is the HDL program for an 2 input OR gate. So here the representation is a data flow model. Assign C equal to A or B, that with that representation will take it as an OR gate. So now the program is there. In the program you start with module and end with end module. Between these two you define your inputs, outputs, and the relation between input output is defined in the equation C equal to A by B, A or B. So that is a simple program. And you know, if you have a OR gate and if you want to test it, what we expect is when we provide 0 at both the inputs of OR gate, we expect a 0 at the output. Otherwise, other combinations like 1 0 0 1 and 1 1, the output used to be 1. This is what expected behavior of our OR gate. So we represent using this HDL code. But if you want to simulate this, we have to write a test bench. So now the test bench is written at the right side. I will show in step by step. So when you write a test bench, initial part of the test bench is the module itself. The test bench also will start with a module and it will specify the inputs and outputs similar to the unit under test. We are going to test OR underscore 2 data flow as our input program, and we need to provide necessary inputs to this program so that we need to validate the output. That is what the testing of this particular program. So for testing the module or the OR gate, we need a test bench. Test bench also, when you write the test bench, you start with module and the name of the test bench followed with the inputs and outputs that will be compatible with the module which you are going to test. So initial part of your test bench is defining the test bench. Second thing is instantiate or maybe take a copy of UUT, that is unit under test. In unit under test, we will take a instance of your program there, that it is named as OR2 data flow, that is a UUT, and and the inputs of here reg J, reg B and reg C are the values of that ABC will be given to the input specified in the gate. So this is how it is represented. The instantiate the unit under test with the test bench inputs. Once these two processes are over, initially define the module, instantiate the unit under test. Then the third process is start giving the inputs so that and monitor the output. So in order to start giving the input, say here you have to start with an initial begin. So your inputs will be given with initial begin and end. Between these two you will give all the inputs. Now from the shaded area it is clear. You are giving A equal to 0, B equal to 0 and wait for hash 100 shows wait for 100 nanoseconds. So you will wait for 100 nanoseconds. By the time the output will be available in the simulator. So once after 100 seconds, 100 nanoseconds, you will change the value from 0, 0 to 0, 1. So then also you will wait for 100. Then again you will give a value for 1, 0. Then again wait for 100 and you give the value 1, 1. So this is how you write the program. The last 4 cases are the test cases. You can test with one, but usually you have a large set of inputs, then you need to find out the best test vectors. Here, since this particular OR gate require only 4 test vectors, we use all the 4 cases here. And the program will end with end and end module. End corresponds to initial begin and end module corresponds to the module test OR. So this is how you write the test bench. In writing the test bench, first you show the entity or the module of test bench, then instantiate the unit under test, then give the inputs in a sequential order. Okay, now if you run the program, in the console you will set some output like this. Here, in order to show the output like this, you have to modify your program with your $monitor or $display. So here the display output which I have shown is obtained by adding an additional program into this test bench. So with this test bench you will not get this console output, but you will be able to get a simulated waveforms like this. Okay, with this test bench you will definitely get a simulated output with waveform shows the x-axis its timing 0 to 100 nanoseconds. Your A and B are low, so the C is low, and from there onwards 100 to 200, 200 to 300 and 300 to 400, any one of A or B are 1, so the C is high after 100 nanosecond. That is the timing diagram that shows the behavior of an OR gate. If this is satisfied, we are satisfied with this timing diagram, then it shows that the code you have written is right. The console at this point, for this particular program, the console will not have this value, but if you write $monitor in the test bench, you will be able to see this console value. Okay, same thing is maybe another program for OR2 with this is a data flow representation of the program. Say you have another program here. Here again the same OR gate is represented with a behavioral model. It's a different way, we will see this later. And for that also you have first test bench is prepared. In this test bench also we have not used the $monitor. Only if you use that $monitor you will be able to get the truth table in the console. So that I will show you when you deal with the programming. So if you want to simulate this in Xilinx ISE newer system, you will be able to get both. But if you use the online simulator, the one which I have sent, the two things I have sent, so there you will get only the console output. There are platforms, online platforms, they support both. That we'll have to find out. For the time being, to start with, you can use the online platform, or those who are comfortable with the system capacity and other aspects try to install this tool, then your learning will be easier. Okay, this is the online simulation link, as well as the links for downloading the tool from the respective websites, and you can install it. Thank you.